Come back. Can we start now? Okay. It's ready. So I would like to call upon Prof. Abderrahmane Nitaj for the second knowledge sharing session. For the title of Analysis of RSA Variance. Please welcome.
Thank you very much. Okay, Assalamu alaikum, good morning, welcome again. This talk will be about RSA, and there are many students here that are familiar with RSA. So if you have questions about something, just ask. So this will be the contents of this talk. First, we will begin by presenting the classical RSA. And also, I will ask many definitions and properties about the curves. And I will present some systems between elliptic curves and RSA. So such systems are mixed and are based on elliptic curves and using RSA models. And I will explain shortly. So the classical RSA system is famous and very easy to understand. RSA was developed by Rivers, Shamir, and Eichmann in 1977. Is the most successful European encryption algorithm and is widely used. And in your project, I am sure that you look at your browser, you can find that your browser or your emails are secure. The security of your emails are based on RSA, mainly on RSA. So the security of RSA is based on they have a problem in number theory. The problem is factoring large integers. So this is the first parameters for the RSA system. The RSA modulus is the product of two large primes. So first, choose two large prime numbers, P and Q, and you can this situation compute and the product of P times Q. Okay, I think this is problem one because it doesn't move like that. Okay, no problem. So the product of n is called RSA modulus, and the prime numbers are of the same size. So the other parameters are function Pn, which is the product P minus 1 times Q minus 1, and this is the Euler's Toscher function. And also another very important parameter is the integer e, which is between 1 and 5n. This is the public exponent, and to each public exponent is a private exponent e, such that the product of e times d is 1 mod 5. So E will be public and D will be private. And the RSA equation, the key equation in RSA is this one, is E times D minus P minus 1 times Q minus 1 times E is equal to 1. And the main goal in attacking the RSA cryptography system is that given N and E, how to find P and Q. You can see here that in this equation only E is known and all the other parameters are private. So it's very difficult to solve this equation. So nevertheless, there are various ways to solve this equation. For example, in 1990, Wiener came up with the method to solve this equation when the parameter d, when the private exponent d is small enough. In this equation, when d is smaller than this bound, then we can find the value of d, also the value of e by applying continued fraction algorithm to e over n and find in this equation the value of d a, and also we can find the value of p and q, which means that RSA is totally broken in this situation. So the method of Wiener is to apply the continued fraction algorithm, and the continued fraction algorithm is an efficient way to find good approximations to E over N. So the approximations are integers such that they are close to E over N. Also, using this key equation, Bonnie and Dirty in 2000 came up with another method to solve this equation by applying Cooper's method. So, their attack is powerful and can solve this equation when D is small enough. More than this bound, and you can see that this improves Wiener's bound, because Wiener's bound is valid for this number 2. In Wiener's bound, this is 0.25, and this is smaller. This is larger than Wiener's bound. In this equation, we can solve this equation and bring the system. So the method of Bonnie and Durfee is based on Cooper-Smith method. Cooper-Smith method, we saw it this morning. It's based on applying the LLL algorithm to solve this polynomial equation. And using this method, we can solve this equation, and we can get the value of x, which is p plus q, and using the fact that n is the product of p times q, we can solve the system and we can find the value of p and q. So also there are many variant RSA equations. For example, this equation is a variant of RSA key equations. Here we have similar equation, but in this equation we have values y, and if we can solve this equation in a similar way, we can find the value of p and the value of q. So Romer and May launched an attack in 2004. This attack can find the solutions of this equation when the parameters x k and y are small enough, mainly for x, x is smaller than this bound. It's similar to the bound of linear, but in this situation, in linear we have, in this situation we have 1, but in here we have any value of y, and we can solve this equation and also get the value of p and q. So the method is a mixed method because they first apply the continuous fraction algorithm to find the good approximations of E over n, and remember that E over n is a perfect parameter, so we can find and we can apply the continuous fraction algorithm to find the approximation P and X, and in this situation, if we find X and K, we can find the other values in this, the other parameters in this equation, mainly Y, P, and Q, by applying Cooper's method. So also, Cooper's method is based on the Abderrahmane algorithm. Also, there are many variants of the RSA equation. For example, we can find the solutions of the key equation if we have extra conditions on the prime numbers. For example, with this difference, if the difference between prime numbers p and q is smaller than this bound, then we can find the value and we can solve this equation and read the RSA system. So these variants are based on this equation or other equations with extra conditions. And another variant of the RSA equation is this one. And in this equation, the extra condition is that the difference between P and Q is, in fact, this term, which is 2 to the n times Q. In here we have a small difference, and in this situation we have a difference which is 2 to the n times some u. Also, there are many other variants of the RSA equation. For example, we can consider this equation and also this equation. In this situation, we can find that here we need p minus 1, and in this equation we need only p minus some u, and also instead of q minus 1, we have q minus some v, and we can apply in this situation the continued fraction algorithm or Cooper's method to find the solutions and to break the RSA system. So, attacking the key equation in RSA or some variants of the key equation are based mainly on the continued fraction algorithm or Cooper's method. The continued fraction of a number, real number x, looks like this. So x is a real number, and the value is 0, e1, and so on are integers and positive integers. So we can find all the values of e0, e1, and so on by applying the continuous fraction algorithm. And we can find very good approximations to the x when we stop the continuous fraction at some level. Also, Cooper's algorithm can be applied to an equation by using this equation to find polynomial and to transform the polynomial to some lattice to reduce the lattice using the LLL algorithm. And the LLL algorithm can reduce the basis in order to find small vectors, and using those small vectors we can find small solutions to mainly this equation or this one or this one, and so on. So there are these are the main variants of the RSA equation. There are other extra conditions that we can use to attack the RSA algorithm. For example, we can use the Chinese remainder variant of the RSA equation, or we can consider many equations like this when we are given E1, E2, E3, and so on. Then we can combine many key equations in order to solve the system of equations and bring the system in some situations. So there are more attacks on weak computing devices such as smart cards. So there are other attacks that are not based on the equation. For example, there are timing attacks, also fault attacks, belt attacks, also other attacks, some strange attacks like such as acoustic attacks, and more general attacks. For example, if you use quantum attacks based on Shor's algorithm, in this situation we can solve completely the RSA system. There are also other attacks such as factoring attacks, and such attacks are mainly based on the general number field C. It's an algorithm that can factor a large number, and also sometimes based on the elliptical method ECM to solve and to factor the modulus if the modulus of the RSA system is of certain form. But in general, factoring attacks can't give the factors of the RSA modulus when the prime numbers P and Q are large n. Also, there are some other kind of attacks called implementation attacks. That means that if the crypto designer makes some mistakes in implementing RSA, then an attacker can use implementation to find the value of P and Q and then break the RSA system. Now I am going to talk about elliptic curves, because in this part we are going to mix elliptic curves and RSA system. So the elliptic curve defined over field. So let's key be a field if, for example, it's true R, C, or a finite field at E. And E1, E2, E3, E4, and E6 are from this field. An elliptic curve or key can be defined by its Weierstrass equation, and the Weierstrass equation with three parameters. The parameter y, c, and x can be like this, and to be an elliptic curve, the main condition is that the discriminant is equal to 0. And, we can compute the discriminant using the parameters E1 to E6. Also, in addition to the solutions of this equation, we have a spatial point at finite point, and it's composed by 0, 1, 0. When you apply 0, 1, 0 to this equation, you can find that it satisfies this equation, and this point is the neutral element for addition. We will see the addition on the filters in the next slides. So if z is equal to 0, you can divide this equation by z to the 6, and this equation you can to the 3, and you can find that you can transform this equation to nothing equation, and the nothing equation of the curve is like this, and we find that the rational points over A are the solution of this equation in addition to the infinite point O. So this is the Weierstrass equation of the curve, and when the discriminant, the characteristic of the field is larger than 2, then we can transform this equation to this one. So this is the short equation of the curve, but also when the characteristic of the field is larger than 3, then we can find finally we can transform this equation to another one which is shorter than the previous one, and this equation we can use E and B to find that the discriminant of the elliptic curve is this one, and the main condition on the discriminant is that it will be different from 0 to get an elliptic curve. So this is these are the equations of the elliptic curve. The first one is general, the second one for P larger than 2, and the next one is for the field with the characteristic larger than 3. When the characteristic is 2 or 3, we can get other Weierstrass equations. For example, when P is P or 3, then we can get this equation. This is 2. I'm sorry, there is no 3 in this situation. So this is possible transformation, and this is another transformation. So there are two transformations for the same elliptic curve. When the characteristic is 2, and when the characteristic is 3, we can find that the elliptic curve can be like this, or can be like this. So these are the shortest equations for elliptic curves, and mainly we are going to work with the characteristic that is different from 2 and from 3. And in this situation, we can find the formulas for addition of elliptic curve. As an example of an elliptic curve of F is this one. So consider this equation, and if you draw this equation, you can find that the points, the real points, are in this curve, and this is our first example of elliptic curve. Also, we can find that there are other kinds of elliptic curves. Mainly this one, we can find that the curve is like this, and also in this example, we can find that the curve of when we draw this equation, we can find that the curve is like this. But you can see that there is a problem in this equation, because in fact we can compute the discriminant, and then the discriminant of this equation is 0. So this is not an elliptic curve because the discriminant is 0. Also, in example 4, we can find another kind of elliptic curves. In this situation, you can see that the curve intersects the x axis, the x axis in 3 points. One here, the second one, the third one, and there's intersections correspond to the solutions of the equation when we write it equal to 0. So you can see that the root is minus 8. This is minus 8. The other root is minus 1. And this is minus 1, and the next one is plus 2. Here, plus 2. So in general, elliptic curve over R is like this, and we can find that points on the curve are on this equation. Also, we can find this curve, and you can see that there is a problem in this point minus 2. But if you compute the discriminant, you can find that also this discriminant is equal to 0, which means that this is not the equation of an elliptic curve. Okay, so we can find when we draw an elliptic curve that there are 3 kinds of curves: the blue one, for example, the blue one, the red one, and the black one. So every equation for each curve here, we can find that we can add points. We can multiply a point by number. We can find opposite of a point, and so on. So in general, we can do some arithmetic using elliptic curves. For example, if we consider the elliptic curve E over field K, how to get the opposite of point P? So the way is to draw the vertical line through P and get in this equation the opposite of P minus P. So in this equation, the point is here, and we draw the vertical line, and we can get minus P as the point in this intersection. So it's very easy to find the opposite of a point when you have an elliptic curve like this. And minus P is just the intersection of the curve with the vertical line. Also, we can double a point if you have if we have an elliptic curve E over a field K. How to get 2 times P when is P is not equal to 0? It means if you have a point in this equation, this is our point P. How to get 2 times P? So it's very easy, because just to draw the tangent line at P, and when we draw the tangent line at P, we are going to get an intersection with the curve, and we draw the vertical line at this intersection, and the vertical line in this intersection will intersect the curve on another point, and this point is 2 times P. So if you have 1 point P, you can get 2 times P in the same curve by using first the tangent line and also the vertical line. Now, if the point P is such that xp is equal to 0, and if you draw the tangent line, you are going to get the vertical line, and the vertical line means that you can't get another intersection with the curve, and in this situation, this means that simply 2 times P is equal to 0. So when you have P with xp equal to 0, close to 0, that means that 2 times p is equal to the infinite point. Now, if you have an elliptic curve E over P, and we have 2 points P and Q, which that P is different Q. So we have P, this point, and Q point, and we need to find what is P times Q, P plus Q. And P plus Q can be found in this equation by drawing the line through PQ. So the line PQ will intersect the curve at this point, and at this point we draw the vertical line. And when we draw the vertical line, we are going to find another point, and this other point will be P times Q. So P times Q can be found by using the line through P as Q, and also the vertical line. And in this equation, we get that the point P plus Q is in this place. Also, we can find P plus Q, but also 2 times Q. We can 3 times Q, and so on. And finally, we can find what is n times Q, and this will give an arithmetic for elliptic curves, and we can use this arithmetic for getting for arithmetic for many properties, and mainly for building vector systems, as we will see later. There are many explicit formulas for finding the composite, for finding the doubling of points, or adding points on the elliptic curve. So in this situation, we assume that we are given an elliptic curve with the short Weierstrass equation over a field phi T, and we are given a point P, this elliptic curve. Then we can find that minus P is simply point xp minus y. Okay, this is not the good sign for the opposite. So the opposite is, you are given a point here, and the opposite will be at the intersection of the vertical line. So the opposite of phi will be in this place. You can see that they have the same x and the opposite y. This is the slide, but it's very easy to see. You can find that minus p is hp and minus yp. Also, there are explicit formula for multiplication, and in this equation we can find this one. For example, we have an elliptic curve and 2 points P and Q, such that each P is different from its Q. Then P plus Q is R. This is R. So this is P and Q. This is the line PQ, and this is the vertical line in this point. And in this equation, we can find a formula for the values of XR and YR. XR will be this, and YR will be this, where lambda is this ratio, and mu is this difference. So there are explicit formulas for computing P times Q that can be implemented efficiently to compute the sum of 2 points on an elliptic curve, or the opposite of the point in the elliptic curve. Now, if we have 2 distinct points, for example, here we have P and Q are different, but they have the same x. So P and Q are the vertical line, and if you draw the vertical line, you can't find the intersection with the curve. So in this equation, this means that P plus Q is equal to 0. 0 is the unit point. And in this equation, this means that P and Q are behind each other. Okay, also for doubling a point, you can find the situation where the point is the x axis, and the situation, if you draw the tangent line will be vertical, and in this situation it means that 2 times P is equal to 0, and we can find the situation that the opposite of P is P itself. Now, if we can also double point P like this when we have P certain point in the curve. So first we draw the tangent line and the vertical line, and we can get 2 times P situation, and we can get explicit formula for multiplication of point P, and we find that 2P is R with coordinates xr and yr. Xr is like this, and yr is also like this, and the parameters for duplicating the point are lambda and b. You can find we can compute these parameters using software for implementing the arithmetic of elliptic curves. So we can find that everything is possible for elliptic curves, for addition, for multiplication by an integer, for doubling a point, for cosine of a point, and so on. And also we can add 2 distant points like this, and in this situation we can find a similar formula. And also we can multiply a point by a certain integer. For example, we have a point P, and we have an integer, positive integer n, and we can find that n times P is this is capital P, n times capital P is P1, it means P n times, and we can use formulas for adding points elliptic curves to find n times P. But in fact, we can compute n times P by using another algorithm, which is very efficient, and to do the efficient way, we have just to write n as in the binary form, and when we write n in binary form, it will be like this, and we can find that n times P will be can be computed by using this method. This method is called Horner method. So Horner method applies for elliptic curves, and it's very efficient to compute n times P. And in cryptography, mainly when you use elliptic curves, we use the product of points with the large number of n. So n times P is important for cryptography, and the easiest way, the efficient way to compute n times P is to use the binary method. Okay, now I'm going to talk about some curves, some elliptic curves through some rectangles. For example, we have an example of a system mixing RSA and elliptic curves. This system is called the K-Mov scheme, and was proposed by Koyama, Moran, Okamoto, and Marston in 1991. It's based on RSA modulus and P times Q. P and Q both are equivalent to 2 modulo 3, and the elliptic curve is this one. It depends on two parameters, parameter A and B, and this elliptic curve can be used modulo. So elliptic curves in general are computed modulo prime number or power of a prime number, but in this situation the elliptic curve is computed modulo n, where n is RSA modulus, and we can find that the arithmetic of this elliptic curve is similar to the elliptic curve on finite field, and here we can use the fact that the number of solutions of this equation, in addition to the infinite point, form a group, and in this equation we can see that the number of points, this is the number of points of E times P, where we use A as 0 and B as 1. We can find that the number of solutions is P times is P plus 1. Okay, this is not the correct this is not the equation. Here we need plus A times X. A times X. So the correct equation is y2 equals x3 plus A times X plus B. So we can find that if we multiply any point in this elliptic curve by P plus 1, we get the infinite point, and we can apply this to any elliptic curve modulo n, where n is the RSA modulus. So if we define E, the elliptic curve modulo n, we can find that when we multiply any point in this elliptic curve by a multiple of EP times EQ, then we are going to get point P. That means that we can use such elliptic curves in order to get raised like this. This is valid for finite field, and this is valid for RSA modulus. So the Klimov scheme is based on mixing RSA and elliptic curves, and the degeneration is very easy. First, we choose two prime numbers, P and Q, such that P is equivalent to Q is equivalent to 2 modulo 3, and we can compute in this equation the product of P times Q as the RSA modulus n, and as for RSA crypto system, we choose a public key E, which is co-prime to P plus Q plus 1 times Q plus 1. You can see that in RSA in general, this is the P minus 1 times Q minus 1. In here we have plus P plus 1 times Q plus 1. And also we can compute the inverse T of A modulo this product, and this is similar to Euler's Tosha function. And we can compute the value of G by applying the same methods than RSA, and the public key will be N and E as in RSA, similar, and the private key will be N and E, also similar to this equation in RSA. Now, how to use K-mod for decryption? So you can see that there is no elliptic curve in the degeneration. So in the degeneration, there is no elliptic curve, only parameters for n and for E for t. So for decryption, you have to represent the message n as a couple m1 and m2, such that m1 and m2 are less than n, so n is public. So we can represent the message n as a couple of numbers m1, m2, and we can use m1 and m2 to compute b such that b is equal to m2 squared minus m1 squared modulo n, and we can find using b, we can find the elliptic curve, and in this equation in here we can find that the elliptic curve is y2 equals x3 plus b, and b will be computed by using only m1 and m2. So with b will be public, but there is no way to find m2 and m1 if we use only this equation, because we don't know the values of the prime numbers that are to n. So n is the product of two numbers, and if you want to solve this equation, you need to know the value of b and the value of u in the models. Also, in order to encrypt m1 and m2, you have to multiply by e using the elliptic curve, and the elliptic curve is in this equation. And when you multiply by e, you get another point on the elliptic curve, and this point can be public because there is no way to find m1 and m2 using the elliptic curve, even if you know that c1 and c2 is e times m1 m2. So this is called the discrete logarithm problem. That means that you know the value of c1 and c2, you know the value of this equation, but you need to compute the value which integral is used to compute c1 and c2. Now for the decryption, it's very easy, because also you know that c1 and c2 are related by this equation. So b is c2 squared minus c1 to the 3 over n, and we can compute the point m1 and m2 by multiplying by d. So we are going to multiply c1 and c2 by d, and we know that e times d is equal to 1 modulo n, and in this situation we can find the exact value of m1. So we can see that there are some public equation. This is the public equation. It came off scheme. It's similar than the RSA equation, but in RSA the difference is -1 here and -1 here, and we can apply also the same techniques to attack such equation. For example, 2008, Ibrahimovic applied the continuous fraction algorithm to find a small solution of this equation. So it's similar to Wiener equation, to Wiener attack, and it solves this equation when the value of d is small enough. Also, we can find that this general equation can be solved when the value of x or z are as 1. Okay, this is ex minus 1. This is a y, and this is a z. So this equation can be solved if we apply the continuous fraction algorithm, or also complex. So So this is the first algorithm that makes elliptic RSA, and also there is another system mixing elliptic RSA. This system is called the Vitko system, and was proposed in 1994 by the Vitko, and it's similar than the K-MOP system. It's built on an elliptic curve like this, and RSA model is like this: P times Q, where P and Q are large numbers. So, in order to apply the Vitko scheme, we first need the mass lemma. Mass lemma says that when we have an elliptic curve by this equation, then we can find that the number of solutions of this equation is the form P plus 1 minus T, where T is smaller than its bound, 2 times square root of P. So this is a very known lemma on the number of solutions of this equation, and we can use this lemma to apply to count the number of solutions of this equation mod n, where n is defined P times Q, and we can find that using the Chinese remainder theorem, we can find that when we multiply any point in this equation, we can multiply by multiple of the number of points in E by the number of points in Q, and we can find that the number will be P because of this dilemma that the number of solutions modulo P times any point in the elliptic curve will be equal to the infinite points. So the Vitko scheme is mainly based on this equation, using RSA modulus, using also mass lemma, and also the Chinese remainder theorem, and for the encryption, something like similar than the previous one. First, in order to find the parameters for the key generation, we choose two prime numbers, P and Q, of similar length. We compute n as P times Q and select two integers E and B, such that the GCD of n and this sum is 1, and this will be the discriminant of an elliptic curve, and we choose integer E such that P, that the GCD of E on this product is 1. Here T, P, and TQ are the numbers that appear in the hash lemma. So hash lemma for P, this is TP, and for Q, it will be TQ. So if we choose E such that E, the GCD of E and this product is 1, we can find and we can compute the number D such that D times E is equal to 1 modulo this product. But here we can see that there is no need for the parameter D, the inverse of E modulo something like this, because in the decryption process there is no need for private key. The private key will be P, Q, and also public key will be N, E, and P. So in the Vitko scheme, the encryption works like this. First, we transform the message N as the x coordinate of a point. The point is P, which is mx, my on the elliptic curve E. So the elliptic curve, as we saw before, the elliptic curve is this one. and we have to transform the message that the first coordinates will be on the curve, and y also the value of y elliptical. Then we can compute the ciphertext C as the product of A times P, and this will be C x and cy, and this is in fact the product of A times this vector and this my use the curve, and when you use this we get another point C, and using the point C we can find the decryption. The decryption is like this. First we compute some term like this, and we compute extra values of Legendre symbols. I hope you know what's Legendre symbol, because we need it for the decryption. Dependent on the value you get for Legendre symbol, you are going to use certain value of t. So, for example, you are going to compute the d if the Legendre symbols are 1 and 1. This is if you get 1 in here and 1 in here, then you can compute d like this, and you can get after you can compute dc, and dc will be de times p, and since de is 1, you are going to get that dc is p, and you know that p is mx and my, and in this situation you are going to get the plain text as before the equation. So it depends on the situation of the Legendre symbol, if it's 1 or minus 1, and you have to compute the value of d, which is the inverse of e, dependent on the Legendre symbols. In each case, we can find the plain text by computing d times c. In every situation, we can find d times c, and we will get the plain text mx and 1. So to attack this scheme, we need, for example, to solve this equation, and this key equation is quite difficult because there are a lot of parameters in it, because we have d, e, u, and v, and this is quite different from RSA equation, and we can use similar techniques, for example, to find solutions of this equation, or we can find we can get a general equation like this with other parameters, many parameters, and we can use Cooper-Smith method or continuous fraction algorithm to solve such equations. Okay, there is another system called PKT scheme, but it's quite similar to the other ones, so I'm not going to present it. I will just say some words about conclusions. Is that RSA is still widely used and also widely adapted, and RSA can be mixed with other schemes, and mainly with curves. And we know that elliptic curves are used mainly in cryptography, and maybe they will replace RSA in the future. Also, many variants of RSA can be studied, and in here in Malaysia, I know that a lot of people are working on RSA, so there is another possibility to study RSA by mixing with the elliptic curves. Well, thank you very much. My explanation. Yes.
secure covalent to the, if we have n bit, right, we have n bit for lattice and n bit for the is it covalent when we use this invisibility for the quantum base? We have quantum computer and n bit, lattice n bit equal to ACC n bit, the secure covalent or the
Even if you use a quantum computer,
yeah.
so quantum computer can solve any problem based on integer factorization or discrete logarithm. So, for example, RSA can be applied also curves, but problems in lattices, quantum computers can't work. So everything based on lattice problems is safe for the moment. And every scheme based on factorization or discrete logarithm will be dead.
Because now there is some clause, then you need quantum computer, right? You get something, you 6 bit or 8 bit already there in the cloud. So that means people can use that quantum computer to break the gates with the.
Depends on the problem for the security. Is it factorization?
So when they say about the quantum computer, how many qubit they're trying to break the system. Now we have, I think, we have 8 bit, I think they over the cloud, we can use it to break the system. Now how many bit?
I think for lattice problems, it does not depend on the qubits because there is no way to apply
For the current system. For the current, now we have an RSA for the 0.8 bit, right? They commonly have.
For how many qubits, I don't know, but for the moment, quantum computers are not used to factor the only one was 15. They factor 15 as 5 times 3. But for the moment, they haven't applied for factorization. So the world is safe for the moment, but we will see in the future. It's okay for the moment.
So there is other question. Right. If you have question, you can ask Professor after the video of the lunch break. Okay. So now I would like to call upon